Okay. Oh, do you hear that? It's so quiet. Because my children are eating right now, and so they're leaving me alone for a minute. Once they're done stuffing their faces, I'm sure they'll come back to bother me. But this will give me the opportunity to start atmosphere. So this module also has two videos. It's the last module that has two videos, I promise. Um, and the reason I split this one into two as well is because I wanted to talk about the atmosphere and then I wanted to talk about weather. And I thought it would be better to split those into two different topics. So this first module, we're going to talk about the layers of the atmosphere, the composition of the atmosphere, how water is sort of incorporated into the atmosphere, air circulation, the vertical atmosphere, and the horizontal atmosphere. Here are some new terms. So let's talk about the layers of the atmosphere. We live in the troposphere. Just above us is the stratosphere. So clouds don't get much higher than the base of the stratosphere. If you've ever looked up into into the sky, on a kind of like puffy, cloudy day, and you see those clouds like get flat at the top, we call those anvil clouds. And that's basically where the troposphere meets the stratosphere. The density changes, and the temperature changes pretty dramatically. So the clouds won't sort of merge into the stratosphere, although there can be clouds in the stratosphere, but these anvil clouds like flatten out. It's really cool. It's really cool to see. Jets reach 39,000 feet. So if you've ever flown in a plane and they're like, we have reached our flying altitude of 39,000 feet. Again, that comes down to a change in density, which keeps which helps the fuel efficiency of planes, basically. Then we have the mesosphere, the thermosphere, the exosphere. So there are multiple layers of this at 5 layers of this atmosphere. We're predominantly going to talk troposphere and stratosphere for the next two videos. But I do think it's interesting to note mesosphere, thermosphere, and exosphere. They're also very, very pertinent and integral parts of our atmosphere. Um, this is a really cool satellite image of Earth's atmosphere that we have a visual of. So this was taken from space by astronauts on the space shuttle, and it shows the thickness of the atmosphere. So here's Earth's surface. It's thick, like it's a thick atmosphere. This is in kilometers, 100 and I don't know, 10 kilometers is sort of this visual thickness of the atmosphere. But again, for the sake of study on weather and climate, we predominantly focus on the troposphere and stratosphere. Noctilucent clouds. That's a fun word. Noctilucent. So above the troposphere. Here's the top of the troposphere. Again, we are living in the troposphere. So just this layer here is the top of where we're living. And that's where planes fly. It's like crazy how thick this atmosphere is. So let's talk about the composition of the atmosphere. Fun fact, and often misconstrued fact, is that nitrogen is the predominant compound in the atmosphere. Everyone's like, oh, it's oxygen, or it's water, or it's carbon dioxide. Nitrogen is actually the predominant gas in our atmosphere, and it consumes predominantly 78% of the atmosphere. Oxygen comes in next at about 21% of our atmosphere is oxygen. Argon, carbon dioxide is this tiny little baby sliver here, and then a bunch of others. There's a whole bunch of other proponents of the atmosphere. And this is from 2017 and it's important to note time because this does change. We are introducing higher levels of carbon dioxide into the atmosphere. Oxygen, when we get to the geologic time or, well, the biosphere module, you guys will have a fun activity where you'll get to see how oxygen levels have changed and carbon dioxide for that matter, how both of these proponents have changed in the atmosphere over time. So they haven't been consistent. It has not been 21% of oxygen consistently throughout geologic history. Um, this composition is the starting point for all things related to weather. And to get weather, we have these elements, these compounds. When we add water, that's when we start to see weather changes. So moisture in the atmosphere, and you can see it in a couple different ways. You might see it in the liquid state of rain, which it's doing right now outside. It's rain, which we need. It's July 2nd. We need that rain. We might see this precipitation in the solid state in snow. We didn't see any of that this year, and I don't think we're going to see it this winter much at all. Sorry, guys. In a gas state, we might not see it, but but it's there. It's in its gaseous phase. And if you're down in the south, you really feel that gaseous phase is as humidity. So understanding how water is presented in these three states of matter, in liquid, solid, and gas, and how they occur and change in the atmosphere is the foundation for understanding weather and climate. How does water change from liquid to vapor? How does water change from solid to vapor? We have some chemical processes. Sorry again for the chemistry. I'm not trying to inundate you with all the chemistry, but it is important to geology. And there are different ways in which these states of matter will change. If we have solid, you might melt into liquid, liquid freezing into ice. Solid turning into gas is this process called sublimation. And uh, okay, you see this in the winter when we have snow, right? If you have a layer of snow and it's sunny out. So it's not actively snowing, but we have a layer of snow and it's sunny out. And you see this like gas sort of coming off of the ice. It's skipping the liquid state and turning that snow directly into a gas. It's sublimating into water vapor. You might have gas that forms solid. This is called deposition. And then from liquid into gas, it's evaporation. And then from gas into liquid, it's condensation. We see this on like water glasses. We see gas in the atmosphere. Oh, wait, I think I said this in another slide. I'm getting way ahead of myself. Okay, I'll show this in another slide. So notice the arrows on this diagram. They indicate the process of how these states of matter change in the atmosphere. We use the term calorie, which is a measure of heat energy. It's energy. Hopefully you're familiar with the term calorie, right? We consume calories. It is a form of energy. But energy, when it comes down to its simplest definition, energy is just heat. And that energy is either released or absorbed as these states of matter are changing. So when we take a close look at the three representations of water, we cannot see them, but understanding the behavior of water molecules is critical for explaining heat transfer and changes in the density of liquid and solid water. So we're going to come back to water. When we think of water as a molecule and we see them in these three different states, we see them either as solid, and when they are solid, they're actually bound together in a crystal lattice structure. So remember, okay, we're going to go back even more to the geosphere and remember that silly argument about is ice a mineral? And geologists like to argue about that and fight about whether or not ice is a mineral because it is technically in a crystal lattice system. This is a crystal lattice system. Minerals might look like this too, because they form this like cubic building block structure. Ice does the same thing. So this is water in its solid form. This is water in its liquid form. One thing you will note that is very, very important to the property of water is that when we go from solid to liquid, it actually gets denser. And this is incredibly rare for a substance to be denser in its liquid form than in its solid form. And the sort of visual of this is when you put ice in your water, it floats, right? Ice is less dense than water. And then when it's in a gas phase, you have these molecules just sort of floating around by themselves, and it's very expansive. Um, they're very apart from each other, or far away from each other. Okay, so this is my condensation. Then I got too far ahead of myself. Okay, yeah, I talked about it, so I didn't want to jump into it. So now we can start to think about moisture in the atmosphere and the occurrence of weather. Weather is entirely dependent on how much water vapor is in the air, and how much water vapor the air can hold. So the following three terms are utilized when we consider water vapor in the atmosphere. The saturation, how much water is in the atmosphere? This is the maximum amount of water vapor that air can hold, and it can hold a lot. The dew point is the temperature to which a parcel of air or a little bubble of air, a little section of air, needs to be cooled to reach saturation or to reach the amount of water that it can hold. So, warmer temperatures can hold more water in this much pocket of air. If you cool this parchment of air, which is my face, you're going to hold less water. So that temperature that this little patch of air sits at is the dew point at which you need to cool it to reach saturation. And then relative humidity is the water vapor content compared to the amount of water vapor required for saturation at the temperature and pressure. So if this little partial of air can hold, I don't know, 50 molecules of water, 25, if we filled it with, okay, let's make this even simpler. If we can hold 100 molecules of water in this little section of air, which is my face, if 100 molecules can fit in here as per the dew point, and that is its full saturation, if we put 100 water molecules in here, that's 100% humidity. If, based on this dew point, only 50 water molecules are sitting in here, that's 50% humidity. And perhaps you're familiar more with like the percentages of humidity, especially as we go into the South. And if you've been to the South, it gets real humid. And if you're at 100% humidity at a really high dew point, it's real sticky. It's not my fave. You could not pay me to live in the South. This glass is sweating. This is what I was getting at. Because the gas on the outside of this glass has water in it. Most atmosphere has some amount of water in it in some capacity. In fact, all atmosphere has some water in any capacity. But when you're in a warmer environment and you're drinking an iced tea here, you get this condensation, and there is this sort of like idea that, okay, well, the condensation is coming from the liquid in the glass, but it's not. The liquid in the glass is so much cooler than the atmosphere that you are in that this hits the sort of the interaction between the temperature of this glass and the temperature of the atmosphere hits a dew point. And this dew point forms condensation on the outside of your glass from the water in the atmosphere, not from inside the glass. So all this condensation is the water in the atmosphere that hits this colder temperature, and that water can't sit in the atmosphere anymore because it hits a dew point. So it condenses from gas to liquid. How cool is that? Oh, chemistry is so cool. So I guess I should have started this in a new topic, and I don't know why I didn't, because the weight of the atmosphere, we're sort of jumping gears here a little bit. Oh, she's back. She's back to terrorize us. You just ate. Like, shouldn't you be napping? Can't you nap? I love you. You can nap in my lap. That's fine. I just need some peace. So the weight of the atmosphere comes down to the different layers of the atmosphere and how, when they're, I guess let's go through the steps so I'm not just screaming at you. Because air is made of matter, which now we have seen, right? It's made of nitrogen and oxygen and carbon dioxide and all these other compounds in it. And it also holds water. So because this air is made of matter, it has a mass, it has a weight to it. And the presence of gravity that it projects on this matter is going to, there she is going to make the weight of the atmosphere heavier towards the base of the atmosphere. So I liked this depiction because what we're looking at are molecules of something: oxygen, carbon dioxide, maybe water, basically the molecules that make up air. they're going to sit closer together towards the surface of the Earth. And then as we get further and further away, those molecules get fewer and fewer and they spread out a little bit more because of the forces of gravity. This concept is known as air pressure. So we have a higher air pressure closer to the surface than we do further away. Another way to think about it is the air is thicker closer to sea level, closer to the surface of Earth than it is up here. It's thinner. And maybe you've heard that too. The air is very thin up here. And that is a true statement in that the molecules present in the air are probably further apart. They're thinner. So the column of air, as it pushes downward, it generates air pressure. Imagine if you have traveled up the mountains and it gets harder and harder to breathe. Another really famous example of this is if you climb Mount Everest, don't climb Mount Everest. It's such a stupid, it costs thousands and thousands of dollars to do, and now there's millions of people that want to do it. It's such a silly thing to die on, okay? Just don't. There are other mountains to climb. But anyways, if you climb Mount Everest, um, people, and if you watch documentaries about it, people will tell you like you need an air mask to get to the top because the air is so thin. You're not consuming enough oxygen. Your lungs aren't getting enough oxygen as they do at surface level here. So this will feed into circulation. So everything we've talked about thus far, composition of the atmosphere, the water saturation, and then air pressure all sort of feed into air circulation. So to understand how air moves and circulates, we do need to think about those proponents that we just talked about, but the other few proponents that we haven't, which is how the sun interacts with the composition of the atmosphere, the water in the atmosphere, and air density. So how do Earth and sun relate to each other in space? How does the atmosphere heat up? How air pressure at a fixed elevation might change? And how air changes temperature without the addition of heat from an outside source. So these four processes combine to get the atmosphere circulating, and they lead to the generation of weather. So ultimately, everything I'm talking about in this video is going to be the lead up to weather, and then climate. Before we go any further on this topic, and I should have brought this up when we talked about hydrosphere, I would like us to at least agree on these four things. Earth is a sphere. I haven't gotten any flat earthers in my class yet, and if you are a flat earther, I do encourage you to set aside, maybe not set aside, but to open your mind into the theory, which is a proved hypothesis, that the Earth is a sphere. We have evidence on multiple data sets that the Earth is a sphere. We also know that oh my God, I can talk, I promise, that Earth orbits the sun. We also know that Earth is spinning. We saw this in the hydrosphere when I had to pull up the spinning Earth GIF to show you. A new factoid, which we will talk more in depth on in the cryosphere module, is that Earth doesn't spin. Oh my God, hold on. Why didn't I bring this down? Okay, Earth doesn't spin. Let me do this completely up and down like this. So here's the equator. It doesn't spin like this. If you've ever seen a globe, we know the globe sits like this. And maybe you're like, well, that's a weird way to have an Earth sit, but it is an accurate representation of the fact that the Earth actually spins on a 23.5-degree tilt. This is important. And it's also really important when we get to the cryosphere module as well. But it is important to note that, especially when talking about weather. If you are unsure about any of these aspects or concepts, please chat with me. It is difficult for an observer to infer these things about Earth. We really need to be in space, or I don't even want to say that in terms of the Earth being round. We have taken measurements on Earth's surface that prove that Earth is round. Henrietta, don't do it. But it is hard to see how the Earth and sun relate without being in space. Oh, I love this question. So think for a moment, if you would, without any research, how do you think the atmosphere warms up? And this feels very intuitive, right? You're like, well, the sun. And you're right in a sense, right? So the sun is on fire. The sun is producing heat, and that heat is generated towards us as solar radiation. And you're like, well, the Earth heats up because of the sun. And you're right, but probably not in the way that you think. The heating of the atmosphere isn't the sun coming into the Earth. Sunlight is invisible to the atmosphere, meaning that these solar radiation waves, so the heat directly from the sun, just goes straight through our atmosphere. It does nothing. It does not interact with our atmosphere at all. Solar radiation travels through the atmosphere. What happens is the Earth is like a sponge, and the Earth absorbs that solar radiation as it comes in. So the solar radiation hits Earth's surface, and the Earth absorbs it. It's like, oh, hey, I'm going to be toasty now. The heat from within the Earth actually re-emits, as we call it, infrared radiation. So it re-emits in a different wavelength from Earth's surface, and that's what's heating the atmosphere. So it looks like this. Here's incoming solar radiation. If we have 100% of this radiation coming into Earth's atmosphere, 70% of that is absorbed by Earth's surface. We have some reflected from the atmosphere, we have some reflected from clouds, and some of it even gets reflected off of the surface of Earth. My son is being really naughty right now. Hold on. Harry. Yeah, I know. You just ate. What's with the drama? So only about 70% of the solar radiation that we have coming from the sun gets absorbed. But that absorption gets re-emitted. So this re-emittance that comes from the Earth is what heats Earth's surface. And if you can imagine, on a cloudy day, if you've ever been outside on a cloudy day, which hopefully you have, sometimes you're like, wow, it's actually kind of warm out today. And then other days when it's perfectly sunny, it's really, really cold. And that's because clouds will work as an insulator. And sort of blanket the Earth as the heat is emitted from Earth's surface. It sort of holds that heat between the clouds and Earth's surface, which is why sometimes on cloudy days it feels warmer. So I like this depiction. It's a little bit more convoluted than this one. This was my like, this is really simple. This is a little more convoluted, but here's our solar energy coming out. And this is basically the re-admittance, the emitting of energy from Earth's surface. And what I like about this depiction too is it depicts, okay, sometimes the heat hits a cloud and it comes back. If we have greenhouse gases, again, we're going to talk more about greenhouse gases in climate change. But when we have greenhouse gases, that might also bounce some of that radiation back into Earth, basically keeping this part of the Earth, the troposphere, very warm. What this means is that, and I love this graph, basically, here is a graph that depicts altitude. So we have Earth's surface here, 0 meters altitude. We go up, we go up. Here's the edge of our troposphere. Here's the stratosphere. And what we see is as we get at the very surface of the Earth, we see very warm temperatures because this is where the heat is being emitted directly from Earth's surface. But as we get higher into the mountains, that heat sort of dissipates into further atmospheric layers. The stratosphere gets kind of weird because as we go higher in the stratosphere, it actually warms a little bit more. And this has to do with greenhouse gases. A lot of greenhouse gases will sit up high in the stratosphere, which is why they're partially problematic. Once you get into the mesosphere, that cools even further. We get real cold. And then the thermosphere is really interesting because it warms up again because some of this does absorb solar radiation up here in the thermosphere. So we kind of go back and forth, but it's important to note that we are really warm at the surface of Earth. And then as we get higher, that heat dissipates out. And this is also why the peaks of mountains are so cool. This is why we see snow on the peaks of many of our mountains, even throughout heat waves. I'm going to surprise you with some more chemistry, but it's because the atmosphere being in a system, it's not closed entirely, but a system that has a blanket, an insulated system, I should say. Imagine a hot air balloon trip is a good way to start thinking about the vertical motion of air in an upward direction. First, the balloon is filled up with cold air to surround the balloon, but then you heat a torch in the center of this balloon, and that balloon assumes a vertical position. The torch continues to add this warm air into the balloon section of the balloon, and it's enough expansion and enough warm air to actually bring the hot air balloon up. This is convection. Remember that hot air rises. So this hot air is now filling this balloon, and this balloon can rise because of the heat. As the air continues to absorb heat within this balloon, it will rise. If you think about infrared radiation from the Earth's surface in the lower atmosphere, that's what we think about. We think about it as convection. So the atmosphere is also convecting, just like the ocean layers did, just like Earth's mantle does. Convection's everywhere, y'all. To translate the hot air balloon analogy into convection, this is just another analogy. And you've seen this boiling water depiction before, where we have heat, the hot water rises, and then the cooler water sinks, and then back and forth and back and forth and back and forth. So this happens with air as well. When we have, hot air, that hot air wants to rise. Now, as we get different densities of atmospheric layers, sometimes this air hits one of these layers and comes back down, and those will form convective cells. So because of this convection, we also see the atmosphere moving horizontally with this vertical movement as well. So this is the horizontal atmosphere spiel. We feel horizontal movement as wind. Ooh, sorry. And this happens in response to differences in air pressure at the surface. So wind can either blow from an area of low pressure to an area of high pressure, or wind will blow from an area of high pressure to an area of low pressure. It usually blows from, I feel like I have a better, maybe it's in my next. Okay, we're going to come back to this question in the next PowerPoint. I've done 3 of these today. I'm so sorry, you guys. My brain is mush. My cats are needy. Oh, Henry has found her napping spot, so that's good. The greater the difference in air pressure, the higher the wind speed. Okay, I didn't want to come back to this in the next slide. I want to answer this now. And I was thinking about an analogy, and I wanted to look it up and make sure this made sense. So, because it's not on my next slide, which is annoying. Maybe I'll put this in the slide and then change the slides. Basically, I guess the best analogy that I thought of is like if you were in a high pressure situation, like lots of homework, and your family situation's a little bit stressful right now, and your personal situation and your work situation and your school situation, you have a lot of pressure. You have high pressure. Your goal is to go from this incredibly intensive high pressure situation to low pressure, right? You want a chill scenario. Everybody wants to live a more mellow, low pressure life. And that's the same in an atmospheric scenario. If you go from a high pressure system, if you have a high pressure system, you want to go to a low pressure system. So that is the natural way in which weather and atmosphere works. And we see atmosphere in different layers of the Earth, like this. These all have different names. This is a better one. Sorry, I'm kind of all over the place, but these have different names. So we call them cells. These sort of high pressure to low pressure scenarios. So these red arrows indicate high pressure systems, and they want to go to low pressure systems. So this is our Hadley cell. This is the cell that's directly above the equator. I don't actually know the names of the other ones. They don't, I'm not going to test you on the names of the cells, but what you do need to know is that at different latitudes, we get different pressure systems that change. Let me go back because I also want to talk about the Coriolis effect again. Remember, I brought this up in the hydrosphere, sort of as a last minute change, but this was where I was going to talk about it initially because it feeds into the atmosphere very significantly as well. So not only when you spin the Earth, the water gyres are going to alter based on the speed of the Earth, based on the location. Remember that the equator has to go much faster to reach the same spot than the poles do. They don't move quite as quickly as the center of the Earth. So as air blows around the surface, it encounters friction and collides with mountains and topography and valleys and the ocean. So local wind can be changed by surface features. But on this global scale, this direction of wind is influenced by the Coriolis effect and the spin of the Earth. Just like this. And here's my video GIF. So because of the spinning of the Earth, this is going to alter sort of the vertical and horizontal movement of the atmosphere. And here we have a high pressure system that's like, absolutely not. I want to go to a low pressure system. And it's convecting because of that. Okay, we're back to this. So heating the lower atmosphere leads to convection, and it also will lead to pressure differences leading to wind, as well as the Coriolis effect. All of these factors go into play to influence the vertical and horizontal movement of air. And this is sort of a depiction of how air moves on a global scale. And I think I show this a better depiction of it in the next slideshow when we talk about weather. Because all of these factors from the beginning of the slideshow, when we talked about the elements that make up the atmosphere, which then will affect the air pressure, which then will also be affected by water saturation and the heat coming from the sun. All of these factors influence the vertical and horizontal movement of air and the atmosphere. And ultimately, what we get then is we get weather systems that are very similar across the same latitude. So that's what the next video is going to be about. Um, so this was your atmosphere video. Stop sharing. And your next video is going to be about bringing all this together and talking about how it turns into weather.